Hi everyone, my name is Madeline Brooks and my project group worked on the design of the Autonomous Mobile Energy System for Ascent Systems Technologies. My team members are Josh Gao, Trevor McKeel, and Marvin Shi, and I hope you enjoy our presentation. The Autonomous Mobile Energy System, or AMES, is a source of renewable thermal energy. Hot water and electrical energy are generated using solar thermal collector panels, or STCs, and a photovoltaic or PV array. The entire system is enclosed in a space small enough to fit into a standard 20-foot shipping container. Some of the intended customers of the AMES are mining camps, disaster relief, and remote communities such as those located in northern Canada. In these communities, approximately 2/3 of the energy consumed is used for heating. Most of this is produced using diesel generators which release greenhouse gases and create health and environmental issues. Renewable heat sources such as the AMES are one of the major pathways for reducing the fuel consumed for heating by these communities. There were several main constraints on the design of the AMES. The first, which is non-negotiable, was that the AMES had to be able to fit within a standard 20-foot shipping container. It must also be able to produce enough electrical energy to supply itself and enough battery bank capacity to run for 72 hours in the event of an emergency. As it is intended to be deployed in a wide range of environments, it must be able to withstand high wind and snow load and a minimum operational temperature range of -40 to 40 degrees Celsius. Finally, the AMES must be able to supply hot water. There is no strict requirement on the amount of thermal energy supplied, but the team made every effort to optimize the thermal supply and energy storage. Verification was done to ensure that the electrical system could supply energy to the devices in the AMES and store enough to last for 72 hours with no incoming solar energy. First, this required calculation of the energy produced by the PV and SDC panels and the energy used by the internal devices each day. The difference between the energy generated and the energy used was found and either added to the battery bank if there was more energy than needed or subtracted from the battery bank if there was more energy needed than could be supplied. This was performed each day for a 2-year dataset, and the results of the analysis were used to determine the size of the battery bank needed and how much it could be discharged before non-essential devices needed to be turned off.
As there would be no appropriate methods to verify the design physically, SOLIDWORKS simulation studies are considered to be the next best choice to verify design decisions on parts and components. Using building simulations in parallel with the design process, the team could verify that the mechanical design is indeed meeting expectations. For example, under an assumed internal load of 10 metric tons, the maximum deflection of the module recorded is only 3 millimeters, while being forklifted. Additional sample results are illustrated on the slide here, but detailed results can be read in the project final report.
Our design accomplishes several of the original project requirements laid out for us, which include electrical energy self-sufficiency, providing a thermal energy source, automatic deployment, as well as structural resilience and long-range control. Some of the future work to be done on the module includes both cost reduction, further battery control, as well as mass reduction and optimization.
The AMES module is far from a generic energy generation system. It is reliable, has low maintenance requirements, and most importantly provides clean thermal energy for users that currently rely on fossil fuel-based energy production. We have met almost all of the main design requirements supplied by Ascent Systems Technologies to produce the design that has been developed from preliminary concepts to a prototype-ready model, with the end goal of hoping to reduce greenhouse gas emissions produced by diesel generator equivalents, with an annual reduction of an estimated 6.6 metric tons of carbon dioxide per module. This is a huge step forward for clean energy production.